Hello viewers, welcome to SK in Design and Analysis of Algorithm. Part 1, we had learned about algorithm and different characteristics of algorithm and how to design an algorithm. Coming to the part 2 of the video, we will be learning about performance analysis. Performance analysis. Performance analysis helps us to select the best algorithm from multiple algorithms to solve a problem. Simple terms, we will be comparing multiple algorithms to find the best algorithm and which is best suitable to the problem. So, what are the performance measurements used to compare two algorithms? Coming to measurement of the performance of the algorithm, we used mainly two measurements. The first measurement is space complexity and the other one is time complexity. Space complexity. It is the total space taken by an algorithm with respect to the input size less the auxiliary space that algorithm uses. Simply, we can say that space complexity is equal to Si plus As, where Si equal to space required for the input and As equal to auxiliary space. Si deals with the space required for the inputs or variables, arrays, etc. So, what is auxiliary space? The extra space that is taken by an algorithm temporarily to finish the work is called as auxiliary space. So, in this way, by adding the space required for the inputs and auxiliary space, we would be getting the space complexity. For example, if an algorithm space complexity is O of 1, it means that the amount of memory it uses remains constant regardless of the input size. And if it is O of n, the space would be growing linearly with the input or the input size. Let's take an example with space complexity O of 1. The example I am taking is Factorial program without recursion. First step, we have to allocate some space to variable x. And let us assume that space required for x equal to 1 unit. And once we had allocated space for x, we no need to allocate the space for x again and again, and we can use the same space. Next, we can see that we had used a variable res. Let us assume res required 1 unit of space. Next, we can see that we are using variable I in the for loop. And let us assume space required for I equal to 1 unit. You can see that we had allocated the space to all the variables. And let us assume auxiliary space required for the algorithm equal to 2 units. By adding all the spaces required, we can see that total space equal to 5 units. And we can see that regardless of the x value, the space is always constant and not increasing. We can see that the value is always 5 units. Therefore, space complexity of the algorithm equal to 5 units. To generalize the space complexity of the algorithm, we can write it as n power 0 into c, where c is a constant. Therefore, space complexity equal to O of n power 0. Since O of n power 0 equal to 1, therefore space complexity equal to O of 1. Now let us take a factorial program with recursion. By comparing the factorial algorithm with recursion and without recursion, we can understand why space complexity is important. In the first step, let us allocate space to variable x. As we already allocated space to variable x, we no need to allocate the space again and again. Let us assume auxiliary space required equal to 5 units. Due to recursive call, the function would be holding the calculation and store the value in a stack. Now, factorial x minus 1 will be called recursively. In return call x minus 1 equal to x minus 2. Since we had already allocated space to x, there is no need to allocate space to x again. But auxiliary space is still required, so we have to allocate the auxiliary space. So now the auxiliary space equal to 2 into 5 units. Now factorial of x minus 2 would be called recursive, and value of x minus 1 into factorial of x minus 2 would be stored in that stack. By repeating the process similarly, we'd be reaching a factorial case where we'd be calling factorial of x minus 1, which can simply be written as factorial of 1. At this point, we can see that the return will be calling 1 into factorial of 0. So now, we would be storing 1 into factorial of 0 in the stack and calling factorial of 0. And now we can also see that auxiliary space equal to x into 5 units. Now when we call factorial of 0, the recursive process will be stopped and 1 will be returned to the stack. Therefore, auxiliary space equal to x into 5 units plus 5 units. In the final step, the function is terminated, and before terminating, all the values are calculated. Now we can see that total space required equal to x into 5 plus 6 units. Here we can see that as the x value is getting increased by 1, 2, 3 and so on, the space complexity of the program is also going to increase. And nature of the graph plotted is a linear line. Therefore, space complexity equal to x into 5 plus 6 units. To generalize the space complexity of the algorithm, we can simply write it as n into c1 plus c2 units. So finally, we can write that space complexity equal to O of n. Before going into the video further, let me ask you a simple question. What is the space complexity of the linear search algorithm, which I had explained in my previous video? Option A, O of 1. Option B, O of n. And the correct answer is O of 1. Let us learn why the space complexity of linear search is O of 1. Let us assume the size of the array is equal to V. Now key value equal to 1 unit. Since we had assumed that array size equal to V, therefore space required for storing an array equal to V into 1 units. Next, n is allocated with 1 unit space. And position also requires 1 unit space. Since we are using a for loop with variable I, therefore we would be allocating 1 unit space to I. And finally, let us assume that auxiliary space required for the algorithm equal to 5 units. So therefore, total space complexity equal to V plus 10 units. When we generalize the space complexity, it is written as n plus c. So then, why would we be considering the space complexity is equal to only O of 1? Here we can see that the space complexity is equal to n plus c due to the array, which we are giving as an input to the algorithm. So most of the time we would be considered that all the input memories are already allocated. So we would be ignoring the n and just write the space complexity equal to c. Therefore, space complexity equal to O of 1. To better understand the space complexity of the algorithm, we would be seeing some more examples in the future. Now, let us learn about time complexity, which is the second performance analysis measurement of the algorithm. What is time complexity? Complexity measures the time taken to execute all the statements of the algorithm, and we should always see that it should be as small as possible, because the more time our algorithm takes, the more cost it is and leads to performance issues. For example, if a statement is executed multiple times and it takes k time for each execution, therefore the total space complexity will be equal to n into k, which can simply be written as O of 1. For example, let us take a simple algorithm which gives the square of a number. Step 1. Identify all the operations performed by the algorithm. Let us assume operation 1 takes t1 time and operation 2 takes t2 time. Let us assume t1 equal to 1 unit and t2 equal to 1 unit. Therefore, total time required to perform the operations equal to t1 plus t2, which is equal to 2 units. We can see that time required is always equal to 2 even when the value of a is being changed. Due to it, we will be obtaining a graph which is parallel to the x-axis, where x-axis is equal to inputs. And we can generalize the time is equal to c units. Therefore, time complexity is equal to c units. Therefore, time complexity is equal to O of 1. Let us take a factorial program as another example. Step 1. Identify the operations performed and if there are any iterators. We can see that there are 3 operations and 1 for loop as an iterator. Let us assume the time required are t1, t2, t3 with respect to the operations performed. Let us assume t1 equal to 1 unit. We can see that there is a for loop in the next statement and it would be running x times. And time required for running operation 2 is equal to 1 unit for 1 execution. Therefore, t2 equal to x into 1 unit, which is equal to x unit, because we'd be running the loop for x times. And in the final step, t3 equal to 1 unit. Now, the total time required for performing all the operations is equal to x plus 2 unit. Here, we can see that as the x value is increasing, the time required for performing the operations is also increasing. When we plot time versus input graph, we can see that it is a linear line. Therefore, time complexity is equal to x plus 2 units. Now, we can generalize the time complexity and write it as n plus c units. Therefore, time complexity is equal to O of n. In this video, we have learned about performance analysis and measurements used for performance analysis, which are space complexity and time complexity. So, this is the end of the video, and in next video, we would be learning about asymptotic notations. Stay tuned for further updates. And please do like, share and subscribe.